All right. Again, and hello and welcome back. Shenandoah. Shenandoah is still watching us. He's keeping a close eye on what's going on here. We are continuing our discussion of it sort of is about the piston robot, but it's a little bit more on the topic of a human mimicking robot that's powered by hydraulics. And my question is, well, what is wrong with that? That's really what we're addressing here. And we would, as usual, we will remember to say hello and welcome. And we're glad you're here. I have a YouTube channel, Patrick Gray. I invite you to subscribe. I think you will enjoy it. There's all sorts of stuff on there, not just robots. I do have a website, and this is piston robot stuff or robot discussion, so you want to stay in this area of the menu. Always reminding everybody anything might be dangerous if it's real. And so if you cannot manage it in a manner that's safe and reasonable and legally allowed, then my suggestion is don't create it. We'll look at these robots on that subject. These metal structures, there's enough strength in these hydraulic cylinders to lift up a 200-pound robot. Just one of them. Right down in through here, there's enough strength. This would be the calf muscle, but there's enough strength in here to push your toe down, push the robot toe down and lift the heel up, and it's on about a 2 or 3 to 1 leverage for a 200-pound robot. That's 600 pounds of force. If you had your finger in there or your hand in through here, it would cut it right off, just like a pair of scissors. And if you were over here on the other side of the robot and managed to get it programmed wrong, and the robot, remember these legs, the robots that I designed, they have the exact range of motion a human being has. So if this robot flexed this leg all the way up, it easily could kick you in the face and hurt you. So I don't mind talking about it. It's interesting as an intellectual exercise, but be careful. This robot could really hurt you. I would not have anybody create this robot unless they're very well versed in robotics. And we can say another issue, I was working on talking about the robot for it to be doing a deep knee bend. And I was working through how much force is needed to get to this deep knee bend. And I can say, if my wife was here, I can tell you, if you have any way that you can keep serious illness away from yourself and your family, you should do that. Serious illness is no fun. Anyway, if my wife was here, I'm pretty sure she would say, wow, that is an ugly robot. And my reply to that is I didn't really design the robot to be pretty. I designed the robot to answer the question, can you make a robot out of physically real parts that is a duplicate of a human being? Can it have all of the ranges of motion of all of the axes of the joints? Can it have, this is a 3-axis joint, this is a 1-axis joint, this is a 2-axis joint. Can it have what human beings have? But I thought maybe the reason nobody has made an actual human mimicking robot where it is a duplicate of the human is that it wasn't possible. And I thought that I would create it using a high quality 3D drawing program So I could establish and show myself, or show anyone who cared, none of these parts are running into each other. You don't have something where something is two different physical structures are in the same place at the same time. And that is done best, I think, with a 3D drawing program, so that everyone that's like, yeah, oh, great, well, sure, you got all this capability, but your robot is impossible. And my answer is, it's not impossible. This could be created. I'm happy to create a FBX export of this. She also, my wife, said, listen, you can't have a robot that doesn't have a head with a face and eyes. And this head is not doing much other than, I thought, okay, I can put a head on it. But it probably would have something to do in a real robot. That's a great place to put the processing system. Now, the robot that I created, this material is aircraft aluminum alloy. This is probably 2205 alloy stainless steel. The hydraulic fluid of this robot does not need to be oil. There's no need for that. Materials exist that can work with water, and so are the pumps. I would have this robot made where the hydraulic fluid was water, so that if the robot needed to be taken apart and something fixed or drained, or you changed how it was, all that happens is you might get some water on the floor. And if you need to refill the system to get it working again, you go over to the sink and get more water. I absolutely would not use hydraulic oil, and it's not needed. There's fire, the pumps used to pump fire retardant chemicals are created not to have to pump oil, particularly at the pressures that we're talking about. The other thing I would say is, particularly if this is 2205 alloy stainless steel, and some of this is, and the rest of it is aircraft alloy aluminum, in my opinion, if you and three of your friends, we gave you this shaft right here, I don't think you could do anything to it. You might be able to scratch it if you had a rock. And the reason I'm mentioning that is, if this robot falls over, as we say we're working on the deep knee bend and just get it wrong, including this arm, it's all design. Every piece of the design that is weak or small or cannot take force, I didn't use that. So if this robot falls over, nothing's going to happen other than, again, my wife would go, so why is the robot lying on the floor? And the reply is, well, I didn't program it right. But it's not going to be hurt. And another issue with this design, particularly with the force and power and speed that you get with hydraulic cylinders, if the robot is lying on the ground on its back, and someone says, so now what? The answer is, well, if you were lying on the ground on your back, how would you get up? And they would tell you. And then you would say, all right. And this robot can do that, because this robot has the range of motion of all of its joints that a human being has. So whatever a human being did to get back up again, this robot can do it. And I think that's exceptionally useful and something that's available with hydraulic cylinder robots, because they have the strength and they have the speed of motion, and they have the leverages and power, and they give you the range of motion that you need, that whatever a human being does to get up off the floor, the robot can do. And I know my wife would be saying, why is everything so big? I mean, that's a set of hips to be proud of. And the reason is, if you put in the abduction, adduction, flexion, extension, internal, external rotation of the human hip that human beings have, it needs to be this wide for this model. I mean, there might be somebody that can do this a different way. And the final thing I would mention is, you can see here with the robot that's standing on the ground, there's the little toe on the right, the big toe on the right, the big toe on the left, the little toe on the left, the heel on the left, and the heel on the right. As long as the center of gravity of the robot is inside of this polygon, the robot is balanced. If the center of gravity of the robot is outside of this polygon, the robot is going to start falling over. And the further the center of gravity is, the faster it's going to fall. That becomes important, I think, from a management of the robot viewpoint. You'll notice when the robot is standing on its foot, you have the little toe, the big toe, and the heel. So the center of gravity of the robot has to be over the polygon, that triangular shaped polygon. And I think the robot, if you look at the weight distribution, it's about right for doing that. And you'll notice, see how it's tilted off to the right? And that is because the weight of the robot has to be over the foot. That's different from where the weight of the robot can be if it's standing on both feet. Notice its head is moving over because when it gets back to both feet, it's standing up straight. And the final thing that we can mention, I would just look at this knee and leg, okay, right here, this articulation. The contraction speed of human muscle is 15 centimeters per second. So it has to move at 15 centimeters per second. It has to do that in 150 milliseconds. The hydraulics people will tell you that the rate of flow of fluid should not be faster than 15 feet per second. So if you know the volume of this cylinder and you know how much fluid you need and you know the rate of motion of this cylinder, it can give you how big the valve has to be in order to keep the flow rate correct. But what I'm showing with this valve is these are 1/8 inch diameter tubing. They are more than adequate to give you that rate of motion for these cylinders. And you might need a bigger valve up here for this one, but the point I'm making is you can give the robot 15 centimeters per second. It's not impossible with hydraulics. Another thing I'll mention is that all of the articulations of the human are leveraged. So this lower leg is about a 7-to-1 lever action against this upper leg. And this is about a 3-to-1 lever action for the foot. So when this is moving at 15 centimeters per second, this is moving at 7 times that, which is where human beings get their speed of motion. And that speed of motion is what allows them to move the way they do, and what allows the robot to walk along in a way different from the way that the rotary encoder robots walk along. All right, and we're going to get into some specific considerations of how is this robot walking like this, but I'm running out of time. I did want to show you one other thing. I wanted to show you that this is the way you have to push these stances together so that the distance from here to here is equal to 1 stride. And that allows you to make the movie of the robot walking along. This is fairly confusing, but I wanted you to see it. And the reason I spread them all out so we could look at the different stances, but in terms of making a movie, they have to be all pushed together like this. And again, I'm getting the secret message, I'm out of time. So we will stop here, and then I will start showing you some considerations of the balance issues that allow a hydraulic robot to work.